Continuing our discussion of the cylindrical capacitor, remember that in part A of the problem we determined the capacitance as a function of x, where x is the distance through which this dielectric was inserted into the cylindrical region. And now in part B, if L is equal to 10 centimeters, the total length of the cylinder, R sub A is 1 centimeters, that is the radius of the solid cylinder inside. R sub B is equal to 4 centimeters. R sub B, remember, is the radius of the hollow cylinder. And capital R is equal to 3 centimeters, that is the radius of the insert. And kappa, the dielectric constant, is 3.21. What is the capacitance when x is equal to 0 and when x is equal to L? And what value of x results in 6 nanocoulombs of charge on the positively charged cylinder plate when the voltage being applied is 1 kilovolts? Okay, so let's look at our answer from part A, and we will substitute x is equal to 0. If we substitute x is equal to 0 here, this term will disappear, and here we will be left with 2 pi epsilon 0 L divided by natural logarithm RB over RA. So we will consider the situation when x is equal to 0. The total capacitance becomes C0, which means there is no insert, and then it will be 2 pi epsilon 0 permittivity of free space total length divided by natural logarithm R sub B over R sub A. This is the situation without an insert. And if we substitute the numbers here, let's do that. We have 2 pi 8.854 times 10 to minus 12, that's permittivity of free space. The length is 10 times 10 to minus 2, 10 centimeters. Let's check that. It was 10 centimeters. R sub B, R sub A, 4 and 1 centimeters. So that ratio becomes 4. Natural logarithm of 4 divided by 1. So if we evaluate this, we will obtain for the total capacitance C total when x is equal to 0 becomes 4.01 picofarads. How about when x is equal to L? So if I look at my answer, when x is equal to L, this term disappears and I will be left with this term, 2 pi kappa epsilon 0 L, natural logarithm capital R over RA plus kappa times natural logarithm R sub B over capital R. So the answer for the total capacitance, C total, when x is equal to L, capital L, is 2 pi kappa epsilon 0 capital L natural logarithm capital R over R sub A plus natural logarithm kappa times natural logarithm R sub B over capital R. And if we plug in the numbers, this is going to be C total when the insertion distance is capital L is equal to 2 pi, kappa is 3.21 times 8.854 10 to minus 12 epsilon 0. The length is 10 times 10 to minus 2 meters. Natural logarithm. Now capital R is 3 centimeters. 3 divided by 1, R over RA, plus 3.21 times natural logarithm. R sub B was 4 centimeters. 4 divided by 3. So this gives me, for C total, when x is equal to capital L, 8.83 picofarads. So let's double check the capital R value here. Capital R value was indeed 3 centimeters. So we want to know the value of x that results in 6 nanocoulombs of charge on the positively charged cylinder plate under a potential difference of 1 kilovolts. Now the relationship between the charge and the voltage is given by Q is equal to C total times V. So we can see that C total will be equal to the charge divided by the voltage, and we're looking for 6 nanocoulombs of charge. So 6 times 10 to minus 9 divided by 1 kilovolts, 10 to 3 volts, that is equal to 6 picofarads. All right, and we're trying to solve for x that gives us this value of capacitance, 6 picofarads. So let's recall our total capacitance. That's the capacitance given here. And we're going to substitute for C total 6 picofarads. So we will have 2 pi epsilon 0 parentheses, you can see here. So we will have 2 pi 8.854 times 10 to minus 12 and L minus x, so that's going to be 10 to minus 1 meters minus x divided by natural logarithm of RB over RA, which is natural logarithm of 4, plus kappa times x, so it's 3.21 x divided by natural logarithm capital R over RA, which is 3, and then we have plus kappa times 3.21 natural logarithm of RB over capital R, which is 4 over 3, and all of this inside this parenthesis, and this must be equal to 6 picofarads. So we will solve for x from this equation. So this gives us 4.01 times 10 to minus 12 minus 4.01 times 10 to 11. Let's not use this cross here because we have an x, and then we have plus 6.37 times, this is 10 to minus 11, 10 to minus 11x, and this is equal to 6 picofarads, 6 times 10 to minus 12. And when I solve for x here, 2.36 times 10 to minus 11 x is equal to 1.99 times 10 to minus 12, 1.99 10 to minus 12, and that gives me x is equal to 8.43 centimeters. That's the insertion distance. So in order to obtain this much of charge, I have to multiply the voltage with the total capacitance, and basically I find the capacitance I need, knowing the charge I'm aiming for, and this gives me 6 picofarads, and I substitute that to the total capacitance, and plugging in all the numbers I solve for x, and the answer is 8.43 centimeters. Alright, so in this problem I have a cylindrical capacitor for which I have solved the capacitance as a function of the insertion distance of the dielectric, which has inner radius r sub a and outer radius capital R less than r sub b. So this is all inside a hollow cylinder, and there is a cylindrical conductor that is basically on the axis of the larger cylinder of radius r sub a, and they all have the same length capital L, but this dielectric as it is being inserted into this hollow cylinder changes the overall capacitance, which is what we did in part A. And then we looked at two limits, x is equal to 0, x is equal to L, so this disappears, or x is equal to 0, this disappears. And we calculated the capacitance for these two limits. X equals to 0 implies there is no dielectric, so it is C0. X equals to L implies there is no air in between the two conductors. And that's our capacitance. So this capacitance as a function of x will be somewhere in between 4 and 8.8 picofarads. And we find that if we're aiming for 6 nanocoulombs of charge, Q is equal to C times V. 6 picofarads of capacitance is what we're looking for, and that corresponds to an insertion distance of 8.43 centimeters.